And we are recording. Excellent. So, well, welcome everybody to this another seminar on the seminar series of complex systems organized by the group of complex systems at Universidad Autónoma Metropolitana. Today we have a special guest, and I have to admit that I'm very thrilled. I'm very nervous that Avi is here with us. I'm going to briefly introduce Avi. So Avi or Abraham Loeb is an Israeli-American theoretical physicist who works on astrophysics and cosmology. Avi is the Frank B. Bert Jr. Professor of Science at Harvard University. He had been the longest serving chair of Harvard's Department of Astronomy from 2011 to 2020. He's also the founding director of Harvard's Black Hole Initiative and the director of the Institute for Theory and Computation within the Harvard-Smithsonian Center for Astrophysics. He has many honors and awards. He's a fellow of the American Academy of Arts and Sciences, the American Physical Society, the International Academy of Astronautics. He was appointed as the chair of the Board of Physics and Astronomy of the National Academy. And also in June of last year, he was sworn in as a member of the President's Council of Advisors of Science and Technology at the White House. And actually in December 2012, Time magazine selected Loeb as one of the 25 most influential people in space. He is a very prolific researcher and author. He has written 8 books or 9 books. I'm not sure if the last one, Life in the Cosmos, is included or not. He also has author or co-author about 800 papers on a broad range of research areas in astrophysics and cosmology, including the first stars, the epoch of ionization, the formation and evolution of massive black holes, the search for extraterrestrial life, gravitational lensing by planets, etc., etc. Also, he has worked on 21 centimeters cosmology, and another thing, he was one of the first one, or perhaps the first ones, who wondered if we would take a picture of a black hole, how this thing would look like. Okay, and recently he published a very interesting book, which is called Extraterrestrial Life, about the Oumuamua. So, and that's why I invited him, because I found what he has to say very fascinating. That's the first point. The second point is like, I like your style, your honesty, the fact that you think that science should not be given by consensus, should be driven by facts. So Avi, thank you very much for being here. So please go ahead.
Thank you, Isaac. It's a great pleasure to be with you. And indeed, what I will be discussing today is the most complex system we know about, which involves intelligence. I don't think we are familiar with any system more complex than intelligence systems. And so let me share my screen and start by saying that all the titles that were mentioned are not so important to me. I basically see science as a privilege of maintaining our childhood curiosity. And therefore, we have this privilege of wondering about the world rather than worrying about our own image. And unfortunately, in academia, this is not very much the practice right these days. But we will get to that later. So what I'll describe primarily is the content of my book, Extraterrestrial, that came out about 7 months ago. And if I had to summarize it with one sentence, I would say, when you are not ready to find exceptional things, you will never discover them. The book was translated to 25 languages. You can see the American version cover in the middle of this slide. There was another book that I published a few months ago, and that is a textbook that you can see on the right-hand side of this slide, Life in the Cosmos, with a former postdoc of mine, Manasvi Lingam. It's more than 1,000 pages long, and it lays the foundation for scientific research on the search for both primitive microbial life as well as intelligent technological life. And what you see on the left side of this slide is a photograph of a photograph that was taken by the German photographer Herlinde Quilbel and presented in the hall of the Berlin Brandenburg Academy of Science and Humanities in October 2020. She came to my office a couple of years ago and asked me to write on the palm of my hand the question that I regard as the most fundamental in science. And I wrote, "Are we alone?" I should say that just a week ago, it was the high holidays of Judaism, and a rabbi sent me an email, as you can see, on September 11th, which is not long ago, telling me that he decided to give a sermon at the congregation in Ann Arbor, Michigan, based on my book. And that was humbling for me, because what it meant is that the content of the book, the discussion on extraterrestrial life, has actually profound implications for religious beliefs of people and existential questions. And a colleague of mine, after seeing that, commented that the next time we meet for dinner, his wife and him will ask me to give a sermon, to which I replied, "I would never lead a congregation whose members agree with me. It's unnecessary." Another thing that happened about a week ago was a call from Congress, the US Congress, to establish a permanent office in the government that will address unidentified flying objects. These are objects whose nature is not understood, not fully understood, and might not be human-made. So that's an interesting development, and the Congress called for doing that within 180 days from now. Now, the one thing I learned after decades of practicing astronomy is that we should be modest. Because now from the data of the Kepler satellite, we know that about half of all the sun-like stars host an Earth-sized planet roughly at the same separation. So not only that we are not at the center of the universe, as advocated by the ancient Greek philosopher Aristotle, and believed for 1,000 years, but by everyone because it flattered their ego, we are not at the center of the universe. But moreover, what we find in our backyard here on Earth is not very unusual. It's quite typical. The Earth-Sun system is common. And there are more habitable Earths in the observable volume of the universe than there are grains of sand on all beaches on Earth. So that should teach us a sense of modesty. We are not special or unique in any way. We tend to think that we are special and unique, but we are wrong. And when you see a painting of an emperor like the one depicted in the middle of this slide, who was very proud of himself after conquering a piece of land here on Earth, you quickly realize, given the cosmic perspective, that this emperor or king was no different than an ant hugging a single grain of sand on the landscape of a huge beach. That's not very impressive. But I can understand where it's coming from. You can see here my two daughters when they were young, and when they stayed at home, they thought very highly of themselves. They thought that they are the smartest in the world. And they are unique and special because they compare themselves to the rest of the family members at home. But when we took them to the kindergarten, they got a different perspective, and they met kids that might be smarter than they are. And obviously they didn't like that. So the only way for our civilization to mature is to meet others. And we know from monitoring the star formation history of the universe, we have data on that, how what is the rate of star formation as a function of cosmic age, the age of the universe, we know that most of the stars formed billions of years before the sun. And if circumstances are similar, if half of the sun-like stars have a habitable Earth-like planet, and if there was even one civilization as advanced as us that existed 1 billion years ago, we are now producing artificial intelligence systems that drive cars and in the future might outsmart us and make medical decisions. So you can imagine sending such a system to space instead of astronauts. An AI system would be autonomous. You can educate it early on in its life through machine learning, and then you send it and it interacts with the world on its own. You don't need to send any guidance to such a system, just like with kids. These could be our technological kids that we can be proud of sending to space instead of astronauts, because humans were not selected by Darwinian evolution to survive in space. We were selected to live here on Earth. So why would we send people to space? That makes no sense. It's sort of like taking a fish out of the water and putting it on dry land. And if you imagine another civilization doing that, let's say 1 billion years ago, sending AI systems into space and equipping them with 3D printing capabilities so they can repair damaged components or they can reproduce themselves just like biological creatures, then such systems could have filled the entire Milky Way galaxy by now. All the habitable planets could be surrounded by probes associated with AI systems that are completely autonomous. They're not getting any guidance from their senders because signals take a long time to traverse interstellar distances. So it makes no sense for a system to be sent to another star and get guidance from the sender. It makes much more sense for the system to be sufficiently intelligent on its own and decide what to do without getting any guidance. Sort of like kids after they become adults. So whether we live in such a reality or not is not a philosophical question. It's actually a question that we can get answers to by looking through our telescopes. And 1 billion years is a long enough time to fill up the entire Milky Way galaxy without a problem, even using chemical propulsion, the type of rockets that we launched already. So we should look through our telescopes to find the answer, whether we live in such a reality. We should not make the mistake that was made by philosophers 4 centuries ago when they said, we know that the sun moves around the earth. And when Galileo said, look through my telescope and you might be convinced otherwise, they said, we don't want to look through a telescope. And they put him in house arrest. Today, they would have canceled Galileo on social media. And what did they accomplish? Well, they stayed ignorant. And we can stay ignorant, no problem. We can say, let's not look through our window. We don't have any neighbors. Let's not check our mailbox. We have no mail in our mailbox. And it could be a self-fulfilling prophecy, a circular argument. If we don't check, we will not know. But that will not get rid of our neighbors. And there could be a package in our mailbox. The fact that we don't check it and argue we don't have any evidence for anything in our mailbox because we don't go to the mailbox, we don't even check it, that will not get rid of the mail that is in the mailbox. And not looking through our windows will not get rid of our neighbors. It's obviously possible to live your life being ignorant. You know, a lot of animals do that. But that's not the type of life I would like to live as a scientist. And so we should not make the mistake of the philosophers during the days of Galileo. We should look for the answers through our telescopes. And that is the basis for the Galileo project that I announced in July this year, just a couple of months ago. Another way to summarize it is extraordinary conservatism leads to extraordinary ignorance. So the idea is to dare to look through telescopes for the answers. And the Galileo project follows two tracks. One is to search for unidentified aerial phenomena of the type that were mentioned in the report to the US Congress just a month before we announced the Galileo project. And very serious people talked about these objects as being real because they were detected by infrared sensors, by optical devices. A lot of military people saw them. So the question is, what are these objects? And if you just use a meter-sized telescope, it can obtain a megapixel image of a human-sized object at a distance of 1 kilometer or so that you can resolve the head of a pin on that object. You can tell if there is a label saying made on exoplanet X instead of a label saying made in China or made in Russia, in which case I wouldn't care less about this object. Also, if we see a bird, I wouldn't care less. I'm not a zoologist. Of course, I will be happy to send the data straight to a zoologist that would study it, or in the case of a human-made object, send it straight to residents of Washington, D.C. who might be interested in that. But both cases are boring as far as I'm concerned. What we would like to find is something unusual. And it's sort of like a fishing expedition. We might find mostly sardines, these fish that are not particularly unusual, in which case, so be it. But if indeed there are objects that are unusual, we want to know about them. And the data will be open to the public, just like a scientific experiment. It will not be classified as the data that appeared in the Pentagon report to Congress. And then the second track of the Galileo project, and I should just explain that this project became possible because a few multi-billionaires came to the porch of my home and asked me questions about my book, Extraterrestrial. And then within a few weeks, I had $2 million in my research funds at Harvard. And, that's quite unusual. I've been department chair for 9 years, and I've been in academia for several decades. I've never seen a situation where a faculty member just gets money without doing any fundraising. So that was quite unusual. At which point, when I had the money, I said, okay, we can establish this project. And then by now, we have a large community of people, of over 70 people involved. The second component of the project is to search for unusual objects that enter the solar system from outside. As I will discuss later, Oumuamua, the first interstellar object that we discovered, was unusual, didn't look like a comet or an asteroid. So we would like to find more. And if we detect them early on their approach to us, a year in advance, we can send a spacecraft equipped with a camera that will take a close-up photograph and tell the nature of such an object. Does it look like equipment? Does it have bolts, screws, or does it look like a rock? Evidence is the key. And as of now, as I mentioned, we have about $2 million for this project. What we really need is more like $20 million in order to do a decent job of surveying the sky. And I hope that more funding will arrive. we have a website at Harvard where you can find more details, including, if you're interested in funding the project, this link that is at the bottom here. So as I mentioned, there was a report on unidentified aerial phenomena to the US Congress, and serious people talked about it, like CIA directors, Brennan and Woolsey, or former President Barack Obama. They said that it's a serious matter and that the nature is unclear of these objects, and it's time for the scientific community to engage in this subject, because it's not a subject that should stay within the talking points of politicians or military personnel that have no scientific training. And it's a very unusual situation where the government, which is the most conservative organization you can think of, is talking about it, whereas the scientific community just ridicules the subject. I don't find that a healthy situation. Instead, the scientists should come forward and say, here we are to help the government and explain something that is not fully understood. And we should do that in the scientific method of using instruments that we have full control over and having open data. So here is the research team of the Galileo project. You can see there are many people involved already within a month or so, and they're very excited about the science that we will explore. And we have also a scientific advisory board. And by the way, I should mention that one member, for example, of the team, the research team, is Alan Stern, who was the PI on the New Horizons mission. Another member of the scientific advisory board is Stephen Wolfram, who created Mathematica.
So actually, Avi, we are going to have a Stephen Wolfram also to give a seminar here, and also Brian Keating, I see them in the list. I wanted to ask you something, if I can. So, yes. In this Galileo project, are you exploring the possibility of training the next generation of scientists? Or, like, for instance, you would have like Mexico students very excited about the possibility of going into this research. Have you considered this?
Yes, I should say that over the past week. By the way, my porch, since I'm on sabbatical this year, my porch became a place where I meet a lot of people. And last week, there was an alum of Harvard University that came to my porch and offered to fund an undergraduate fellowship for summer research that will be endowed and allow an undergraduate student to work on science related to the Galileo project. And just before that, I had another visitor who was interested in funding a postdoctoral fellowship related to the Galileo project. So definitely there is a component of this project that will train young scientists, because I mean, one of the main reasons I wrote my book is to encourage young people to enter science, because science doesn't need to be boring. You know, it doesn't need to address questions like how many angels can sit on the tip of a pin. What theoretical physicists are discussing right now is not exactly that, but are discussing like how many extra dimensions are there? What is the string theory landscape? These are questions that are not very different from how many angels can sit on the tip of a pin, because we have no way of testing them experimentally at the moment. We have never seen a clue for these ideas. And the multiverse is not something we can visit. And so these are subjects that are part of the mainstream in theoretical physics, and are very removed from any implications to our daily life, from any experimental test. And that they're removed not by coincidence, they're removed on purpose, because they're being used as the sandbox for theoretical physicists to demonstrate that they are smart. They're doing in mathematical gymnastics and showing how smart they are by manipulating formula. But this sandbox has no direct relevance to the reality that we live in. And, you know, that doesn't need to be the face of physics. The face of physics could be relevant to our lives. And if we see objects that are unusual, studying them is relevant to the future of humanity. And guess what? A lot of young people are excited about it. And guess what? When I wrote the paper, when I wrote the book, I got a huge response from the general public. The book became a bestseller in many countries. And after announcing Galileo project, I got thousands of emails from people interested in contributing to it. So with the Galileo project, I basically proved my point that we can bring new funds into science by discussing this subject, and we can attract young people into science by discussing this subject. And nevertheless, there are a lot of people in the scientific community still, after the Galileo project was announced, that have a problem with that. Now I ask you, how is it possible if I bring money that was not allocated to the search for dark matter, or some other, or the search for the exact value to a second decimal point of omega matter, or the kind of things that are funded in science? I'm not taking money out of that, even though the search for dark matter, for 4 decades didn't really discover the answer, and hundreds of millions of dollars were invested already. It's a search in the dark. I haven't taken money from that. And moreover, we are establishing a project that is aimed at collecting evidence. It's just data driven. It's not speculative. We're not talking about, the multiverse that we have no chance of visiting. Nevertheless, we are seeking data. We are using money that was given just for that purpose. Nevertheless, scientists have a problem with that. And I ask you, how is that possible? If the subject is relevant to the public, and the public funds science, isn't science supposed to echo the public's interest? And instead, what you find in academia is that a lot of the people that have tenure are basically pursuing honors and awards. And, if they get a lot of likes on Twitter, then that's a very beneficial, response for them, because it shows that they get the respect of their colleagues. But science is not supposed to be about that. Look at the example of Galileo. It's not supposed to be about being liked by whatever the mainstream thinks at the time. It's supposed to be guided by evidence. And it's supposed to encourage people with tenure to deviate from the comfort zone and explore risky propositions and try to carve out new territories for research. So I'm frustrated by that part, that science is not, the academic climate is not really nurturing what it's supposed to nurture.
Which is like we should behave like children, right?
Yeah, well, exactly. Yeah, I have. If you ask people that know me, I haven't changed much since the time I was a child, and I'm proud of that. I refuse to surrender to reading how many likes I have on Twitter. I don't have any footprint on social media.
Yeah, I know about that from your book. That's right. No, I agree with you. It's kind of puzzling, the whole situation. And yeah, it has happened in the last couple of decades that academia is not working properly. No.
Yeah, well, I'm trying to change this climate, but it's not an easy thing, because if you were to approach Marie Antoinette, during the French Revolution with the principles of the French Revolution, you wouldn't get much response, right? Because she benefited from the old system, right? And so the people that I'm trying to approach benefit from the current system. They benefit from the culture that says that you are supposed to demonstrate that you are smart more than you are supposed to describe nature. Okay, and because they benefit from that, there is a lot of resistance. I can give you an example. There was a colloquium about string theory, where the speaker, a prominent leader, was talking about a connection between the string theory landscape and cosmic inflation. And I said, great, now suppose we test your version of cosmic inflation using the cosmic microwave background and demonstrate that it's not consistent with that version, the data that we obtain. Would that prove string theory wrong? And the person said, no, it will just prove my conjecture of that connection being wrong. So I asked, what is the point here? You know, you're making a conjecture, giving a full colloquium on it, writing lots of papers on this connection, and at the end of the day, string theory will always be right. So the point is, many scientists don't put any skin in the game. They don't make a prediction that can be proven wrong, because then it will damage their reputation in some way. So it's best to be in a place where whatever you say doesn't really change anything, because it's not being tested. And I say that's a betrayal of the tradition of physics. You know, Einstein was wrong 3 times in the last decade of his career. He predicted that gravitational waves do not exist. He wrote a paper about that. That was wrong. He argued that black holes do not exist. That was wrong. And he argued that quantum mechanics doesn't have spooky action at a distance, which today we call entanglement. That was wrong. And it just shows that if you are working at the frontier, you know, even though you are an experienced, most celebrated scientist of the century, you can still make mistakes. But that's part of the learning process. So why would scientists shy away from this learning process and say, you know, we prefer to be in a place where we are never tested, when we are always right because our predictions cannot be proven wrong, and where we can give each other awards and honors and, you know, and be happy that we are, we show that we are smart. You know, to me, it's just like the situation with Bernie Madoff. You know, he told people, give me your money, and they were happy to give him his money, their money, because he said, I will give you back in return more than you gave me, irrespective of what the stock market does. And they were happy about that. They gave him the money. He was happy that they gave him the money. And then when the experiment was done and they asked for the money back, he was put in jail. So an experiment is not just a test that is a nuance of doing physics. It's actually crucial for doing physics, because you can avoid Ponzi schemes this way. Anyway, we are going on a detour here. Let me continue.
Please go ahead.
So we have also a philanthropic advisory board, a public outreach group, and a lot of research affiliates to the Galileo project. And the central question is humanity's future, because currently all our eggs are in one basket here on Earth. And if a catastrophe takes place, all of these eggs will be destroyed. So you might remember this biblical story about Noah's Ark, where Noah, according to the Old Testament, built an ark where he put animals that will be saved from the great flood. And so we can avoid the catastrophes here on Earth by building a spaceship that will include an AI system where we put the DNA of all the forms of life that we care about, and we can, in principle, reproduce them in other locations if we know how to make synthetic life, which we are getting close to doing right now. So I call it Noah's spaceship. So currently, Earth is our home, but only for a short time. I should say that this statement is not true for everyone. The ashes of Clyde Tombaugh, the discoverer of Pluto, were sent on the New Horizons spacecraft. And that was not a very scientific thing to do, because what are ashes of a person? You take the DNA of a person and you burn it up, so it doesn't carry any more information. That doesn't make sense to send no information when you try to celebrate a person. They should have sent, NASA should have sent the genetic code of Clyde Tombaugh in electronic form, or maybe a stem cell on that New Horizons spaceship to celebrate Tombaugh. If another civilization finds that New Horizons spaceship and finds that the ashes, they would laugh at it, because how can you celebrate a person by sending no information whatsoever about the person? These ashes are no different than cigarette ashes in an ashtray. They carry no information. So why would NASA do that? I don't know. I actually asked the PI on the New Horizons mission about that. At any event, the threats that we face include internal threats, self-inflicted wounds, such as changing the climate, wars, pandemics, or technological catastrophes, as well as external threats, such as asteroid impacts. You know, within 1 billion years, the sun will boil off all the oceans on Earth. So it will burn up also all the monuments that we built around. When I go around Harvard University, I usually find paintings and sculptures of former presidents and deans that wanted to preserve a copy of their physical appearance, but that will go away when the sun will burn up the face of the Earth. And the only way to maintain a monument that lasts for longer than the sun is to send something into space, an avatar of ourselves, like an AI system. So let me mention in a few words my personal journey from being born on a farm to space exploration. I was born 59 years ago in 1962. You can see a photo of me at age 6 on the top left. And then I used to collect eggs every afternoon. We had chicken. You can see me on the second image on the left. And I was primarily interested in philosophy at that time because it addressed the most fundamental questions, although it didn't give good answers to those questions. So I used to drive the tractor to the hills of the village and read philosophy books. You see me next to my sisters on a tractor in the middle top photo. And then one thing led to another, and I ended up as chair of the astronomy department at Harvard. And in May 2015, a black limousine parked in front of the Center for Astrophysics at Harvard. And out of it came an entrepreneur from Silicon Valley named Yuri Milner. You can see him in the bottom left. He came to my office and asked me whether I'm willing to lead a project whose goal is to visit the nearest star within our lifetime. So that meant within 20 years or so, since both Yuri and I are of the same age. I knew that the nearest star is 4 light years away. So it takes light 4 years to traverse the distance. If you want to get there in 20 years, you need a spacecraft that moves at 1/5 of the speed of light. And that's 1,000 times faster than the chemical rockets that we produce. So that's a big jump in speed, as big as the jump from the T-car that Henry Ford produced, the first commercial car, and the Sputnik, the first satellite that we sent. But I thought about it for 6 months, and I came up with one technology that could potentially do the job. And we announced it in April 2016 in New York City in the company of Stephen Hawking and Freeman Dyson, as you can see from the bottom middle photo. So this is an artist's illustration of the solar system. You see the sun on the left and the nearest star system, Alpha Centauri, on the right. The nearest star to us, this is a 3-star system, and the nearest among them to us is Proxima Centauri. And the solar system actually extends halfway to that star. Most of the volume is associated with the so-called Oort cloud, which includes the building blocks of the planets. These are rocks that sort of like bricks left over from the construction project of the solar system. And they are rocky objects that are covered with ice that were scattered around the solar system during the formation process. So the nearest star is actually a dwarf star, Proxima Centauri. It's 12% of the mass of the sun, and it's much fainter than the sun, and it has half the surface temperature, so it emits mostly infrared light. And it so happens that there is a planet roughly the size of the Earth, 20 times closer to the star than the Earth is from the sun. And that's roughly the distance where you can have liquid water on the surface. And this planet is so close to the star that it's tidally locked, just like the moon is. So the tidal gravitational force keeps the same side facing the star at all time. As the planet moves around the star every 11 days, there is a permanent day side and a permanent night side. And my daughters say, if we ever go there, they would like to have a house on the strip that separates the day side from the night side, because you can sit on the porch and watch the sunset forever. Just think about it. The sun never sets on that strip. Now, since this star emits mostly infrared radiation, I asked the students in my freshman seminar class at Harvard, do they know of an animal on Earth that has infrared vision? And one of them found this image of a shrimp whose eyes are like ping pong balls connected with cords to the head of the shrimp. And she said, it looks like an alien to me. Now, how do we get there? Well, the idea is to use a sail, a thin film of material that is pushed by light. And because of that, it doesn't carry any fuel with it, and it can reach the speed of light, in principle. And one can attach electronics that you find in the guts of a cell phone, like a camera, a navigation device, communication device, to that sail. And if it weighs roughly a gram and the laser is very powerful, roughly 100 gigawatt, you can accelerate it to a fifth of the speed of light within a few minutes. So here is an illustration of how it works. There is an array of low power lasers whose beams are combined to make a very powerful laser beam that shines through the atmosphere and pushes on a sail that is released above the atmosphere so that it doesn't encounter the friction with the atmosphere. And then the sail is being pushed for a few minutes by 100 gigawatt laser. And if the sail weighs a few grams, it would reach a fifth of the speed of light across a distance that is 5 times the distance to the moon. So the launch phase is a few minutes, and then the trip, the journey, takes 20 years. That's a very long journey. And the idea is that once we get there, and we should aim at where Proxima Centauri will be 20 years from now, once we get there, we can take a photograph of the planet, the habitable planet next to it, and check whether there is life on it. And the signal associated with this photograph will take 4 years to reach us. So altogether, 24 years. That's a long time, even for the nearest star. We need a long time before we will find out what's out there. Now, to reach close to the speed of light, you don't need to use a powerful laser. In principle, you can use a natural source of light, such as an exploding star. So turns out that if you park a light sail, like the star shot concept, within 100 times the Earth-Sun separation from a massive star that is about to explode in a supernova, the flash of light that is generated by the exploding star can carry the sail up to the speed of light. And sort of like these surfers on the beaches of Hawaii that are waiting for a giant wave to carry them. Except here, the wave is a wave of light, a flash of light. And another analogy is dandelion seeds that are carried by the wind, as you can see on the right side here. So the question is, are we really the smartest in our cosmic neighborhood? Are we the sharpest cookies in the Milky Way jar? And my guess is probably not, based on the news that I read every day. The way I define an intelligent species is as a culture that shares evidence-based knowledge. And that's not what we do on a daily basis. We don't share much. The best example is the COVID-19 pandemic. Started in China. There was not much sharing of information with the rest of the world. And a lot of lives could have been saved in the process. So politics very often interferes. And if you look at politics, you don't see a lot of examples where it's based on evidence. So we still have a long way to go before other civilizations will regard us as intelligent. And without prejudice, we should just be open-minded to find other kids on our block. And the best place for us to search is in our backyard, in the solar system. Turns out that the first object discovered from outside the solar system near the Earth was found in October 2017 by the Pan-STARRS Observatory on the summit of Haleakala Mountain in Maui, Hawaii. And it was given the name Oumuamua, which means a scout in the Hawaiian language. You see this object circled in blue in this image, where the background stars are moving relative to it. And this object at first was thought to be a comet. If it came from another star, probably just like the objects in the Oort cloud. But it was not. And in fact, it started from a very special frame of reference called the local standard of rest, which is the frame that you get to when you average over the motion of all the stars in the vicinity of the sun. Sort of like the local galactic parking lot. And Oumuamua was at rest in that frame. Only 1 in 500 stars is so much at rest as Oumuamua was. And if it came from any of the nearby stars, it would have inherited the motion of that star relative to the local standard of rest. So it clearly did not originate from any of the nearby stars. And it behaved just like a buoy sitting at rest on the surface of the ocean. And the sun, the solar system, like a giant ship, bumped into it. And as the object was tumbling every 8 hours, the amount of sunlight reflected from it changed by a factor of 10. That meant that it has a very extreme shape. Projected on the sky, it was at least 10 times longer than it was wide. And then when the reflection of light was modeled, it looked like a disc shape is favored at the 90% confidence over a cigar shape. What you see in these two plots are diagrams showing different orientations of a disc or a cigar that would reproduce the observed light curve, and a dark black color implies a high likelihood. And you can see that for the disk case, there is much more of parameter space that allows to reproduce the light curve. So at the 90% confidence, this object was pancake-like. And then when the Spitzer Space Telescope looked at this object, there was no detection of gas or dust around it. Not only we didn't see a cometary tail, as you expect in the case of a comet. The comet is just an icy rock that when it gets close to the sun, the ice evaporates and you see a trail of gas and dust around it. There was nothing visually, but moreover, the Spitzer Space Telescope put very tight limits on the existence of carbon-based molecules around it. And you can see the image from the Spitzer Space Telescope on the top right. There is basically nothing in that image. It didn't see anything. And that puts very tight limits on the existence of any evaporated gases. So it meant that this is definitely not a comet, the way astronomers thought originally. It's not a comet of the type that we have seen before. But at the same time, the object exhibited an excess push away from the sun, non-gravitational push. And given that it could not have had the rocket effect from evaporation, the question is, what provided this excess push? And the only thing I could think of is the reflection of sunlight, because this push declined inversely with distance squared, just like you expect for reflection of sunlight. And it changed smoothly with distance without any jitters or any cutoff beyond the ice sublimation distance. So in order for sunlight to push such an object to be effective at doing that, this object had to be thin, very thin, like a sail. And nature doesn't produce thin objects like that. So I suggested maybe it's artificial, like a plastic bag flying in the wind, you know. And so that's the fundamental question. Is Oumuamua natural, a rock, or is it artificial? Turns out that in September 2020, after I finished writing my book, actually, there was another object discovered by the Pan-STARRS telescope in Hawaii, the same telescope that discovered Oumuamua. And this object was given the name 2020 SO. It was thought to be an asteroid, but then it showed an excess push away from the sun by reflection of sunlight, and it didn't have any cometary tail, just like Oumuamua. But shortly afterwards, the astronomers realized, oh, this object actually came from Earth. If you extrapolate the trajectory back in time, you find that it was launched in 1966. And in fact, it's a rocket booster that was part of a lunar lander mission that we launched, NASA launched. So it had thin walls, and that's why it had a large area for its mass, and it was pushed by reflecting sunlight. So we definitely know that 2020 SO was an artificial object because we made it. The question is, who produced Oumuamua? And as I said before, there were a number of anomalies about Oumuamua, the first interstellar object we discovered. We didn't expect it to be there because I wrote a paper a decade earlier that the number of rocks that we should see from other stars is too small. We wouldn't see any with the Pan-STARRS telescope. It originated from the local standard of rest. Only 1 in 500 stars does it. Its brightness changed by a factor of 10, which meant a very extreme shape. And the best shape was that of a pancake, quite unusual. And then it deviated from a Keplerian orbit without outgassing. There was no cometary tail. And so I suggested it's being pushed by sunlight. But other scientists, other astronomers tried to explain Oumuamua as a natural object. And all of the suggestions that were made invoked something that we have never seen before. For example, a cloud of dust particles that are very loosely bound, 100 times less dense than air, so that it's a very lightweight kind of object that is pushed by reflecting sunlight. The problem with that is, if you imagine a cloud that is 100 times less dense than air on average, it would not maintain the integrity when it's heated by the sun to hundreds of degrees. Then there was a suggestion, maybe it's a chunk of frozen hydrogen, so that when hydrogen evaporates, you don't see it because it's transparent. And the problem with that is that hydrogen evaporates very easily. So it would not survive more than a few million years in interstellar space and would not survive the journey from large distances. So then there was a suggestion, maybe it's a nitrogen iceberg chipped off the surface of a Pluto-like planet around another star. And here the problem is there is just not enough nitrogen, solid nitrogen out there. And we did the calculations of both the hydrogen iceberg, the nitrogen iceberg, and showed that within a few million years in both cases, you would evaporate them as a result of absorbing starlight or cosmic rays. And there is just not enough nitrogen to explain Oumuamua.
Avi, this last paper that you mentioned about nitrogen too, is this where they claim that this object came from the Kuiper belt, right?
No. We, in the solar system, we've never seen a nitrogen object made of pure nitrogen. We've never seen. So all of these suggestions are of something we've never seen before. So in the case of nitrogen, they would argue, oh yeah, there are other environments that make nitrogen icebergs, and they provide a lot of them. They are not like the solar system, because somehow in the solar system, all the nitrogen icebergs were evaporated by now. We don't have anything left, but there are younger stars out there, that are 10 times younger than the solar system, and in them, the nitrogen icebergs survived, and we are seeing one of these objects. The problem is, if you go through the math and you include especially if you include cosmic ray evaporation, there is just not enough nitrogen available in all the. If you take all the nitrogen that you find in stars and put it in this solid form, and there is just not enough. So this makes no sense. Not to speak about the fact that we've never seen a nitrogen iceberg. We've never seen a hydrogen iceberg. This is a paper just from last month, written by the people who proposed the hydrogen iceberg. And I highlighted the middle sentence from the abstract. You can find it on the archive. And it says that the hydrogen and nitrogen models have serious difficulties. Okay. So, my point is, we've never seen these things. And, most of the time when we walk on the beach, we see rocks or seashells that are naturally produced. But every now and then we see a plastic bottle. So that's the analog of Oumuamua, in my view. And it implies the existence of a civilization that produced it. Now, if you imagine a caveman finding a cell phone, the caveman is used to playing with rocks, and therefore will argue that the cell phone must be a shiny rock of a type that we have never seen before. Just like astronomers would argue that Oumuamua is a rock of a type that we have never seen before, like a hydrogen iceberg, a nitrogen iceberg. We don't know if there are any hydrogen icebergs out there. We've never seen any. We don't know if there is a process that makes them at all. It's a complete speculation. And nevertheless, the people who argue, oh, Oumuamua must be natural, are very convinced that it must be natural, even though we've never seen it. Now, of course, it's the beginning of a learning experience, because the caveman may press a button and realize that this shiny rock records his voice. And he may press another button and realize that it records his image. And then it will become clear that it's not a rock. But that is possible only if the caveman is open-minded to collecting more evidence, rather than arguing business as usual. And so, we should aim to press buttons on rocks like Oumuamua if they look nothing like we have seen before, rather than declare business as usual because they must be either a nitrogen or hydrogen iceberg, case closed. I should say there was another object that looked like a comet and came from interstellar space. It was discovered in 2019, and it was named Borisov, after the amateur astronomer that discovered it from Russia. And I was asked about this object by people who said, oh, it looks just like a regular comet. And I said, yes, it is. It must be natural. So they said, well, doesn't it convince you that Oumuamua was natural as well? And my reply to that is, if you walk on the beach and you see a plastic bottle, and after that you see a rock, it doesn't make the plastic bottle a rock. On the contrary, it convinces you that the plastic bottle is different because it doesn't look like the rock. So they say a picture is worth 1,000 words. In my case, a picture is worth 66,000 words, the number of words in my book, Extraterrestrial, because I wouldn't need to write the book if we had a high-resolution image of Oumuamua, like the one you see in this slide. This was taken by the OSIRIS-REx mission that not only took the picture, but also landed on the asteroid Bennu and collected the sample that it will bring back to Earth in 2023. So just imagine landing on an artificial object. We could easily tell the difference between a nitrogen iceberg and a technological piece of equipment that has bolts and screws on it. And if we press some buttons, we might be able to learn about the technologies that operate these things. One thing to keep in mind is, we are born into this world like actors put on a stage, and we tend to think that the play is about us. But one thing to realize is we are not at the center of the stage. The universe is 10 to the power 26 times bigger than the size of our body. And the play has been going on for 13.8 billion years, since the Big Bang. We just came at the end. The play is not about us. So we should be humble, modest, and try to learn from other actors that may have been around longer than we did. And one way to find whether other actors are out there is to search not only for relics, but for industrial pollution in the atmospheres of other planets, to look for city lights in the night side of Proxima b, the planet around Proxima Centauri. These are subjects that I wrote papers about in recent years, to look for photovoltaic cells, the reflectance from them on the surfaces of planets, to look for light beams that are used for propulsion of light sails, and so forth. And there is this famous paradox by Enrico Fermi: where is everybody? And that is, of course, very presumptuous of us to ask, where is everybody? Why would we assume that we are sufficiently interesting for someone to come over and have a party in our backyard? Most likely they don't care much about us, because we are just like one ant out of many that existed on the sidewalk of the Milky Way galaxy over the past few billion years. We are not special in any way. And moreover, many of them must be dead by now, many of these civilizations that predated us, because we know it from experience that as soon as we develop technologies, we also develop the means for our own destruction. And so we will have a short lifetime if we change the climate on Earth or do other damaging activities. So there may be a very short window of opportunity to find others. But we should search. And the analogy I make is with archaeology. Even though many cultures that exist before us on Earth are not around anymore, we can find evidence for them by digging in archaeological sites. And the same you can do in space. You can find relics, artifacts that were sent by those civilizations. And my hope is that by finding those relics, we will have a better future, because if you look at human history, much of it was shaped by a group of people trying to feel superior relative to other people. The best example is the Second World War, where the Nazi regime triggered the death of 75 million people. That was 3% of the world population in 1940. And it's 20 times more than the number of deaths triggered by the COVID-19 pandemic so far. So just think about it. 20 times more people died just because a group of people decided to feel superior relative to other people. And if we find evidence for another civilization that is far more advanced than we are, then all our genetic differences would appear laughable, insignificant. So my hope is that it would inspire us to ignore our small differences and cooperate as equal members of the human species. Thank you.
Thank you, Avi, for this very fantastic seminar. I know that you are very, very busy. So first of all, once again, for being here. Do you have time to be around so we can ask you some questions?
Yeah, please, go ahead. You can ask me.
So, colleagues, if you have some questions, just there are two ways to do it. Just write it on the chat and I can read it, or just directly unmute the microphone and ask directly to Avi.
Why don't you read it? Yeah, go ahead.
Yeah. So in the meantime, so let me ask you a couple of questions. I wanted to ask you a personal one, if I'm allowed. So how do you manage to keep your cool, let me put it that way, after all the videos you have received? And how do you manage to keep being so efficient? Because, you know, I've organized many seminars, I invited many people, and you are one of the first ones that as soon as I push the send button, you reply immediately. How do you manage to do this?
Well, I keep my desk clean. I don't postpone. You know, I don't take, in a military analogy, I don't take hostages. I don't leave things alive in the background that I have to take care of later on. I basically respond immediately to all the important requests that I get. And I work around the clock. You know, I wake up every morning at 5 a.m. I usually jog in nature early on. And after that, I work most of the time. And the other thing is I take seriously every person, you know, irrespective of their status or their origin. And just because, you know, I know for a fact that I came from a very non-typical background. You know, I was born on a farm. I ended up tenured at Harvard, but I actually resonate more with people that do not have formal education and people that, you know, and so now in terms of efficiency, you see, that's something I haven't quite figured out, but I was department chair for 9 years. And when I started, the previous department chair told me it will take 85% of your time. It ended up taking 15% of my time. And the way I see it is just like driving on the highway. If you don't take the wrong turn, the wrong exit, then you can be very efficient. If you take the wrong exit in the highway, you will have to spend a lot of time getting out of there and trying to figure out what to do. And it's really important to make the correct strategic decisions when you decide about things. And that's what allows me to be efficient. I see the solutions relatively immediately, you know. So there was a recent example where I gave a colloquium, you know, I gave about 6 colloquia over the past 2 weeks. And it started with a colloquium at the University of Connecticut. And after that, an MIT professor, Walter Lewin, approached me and said, you know, there is a problem that I've been thinking about for 3 years, and it bothers me. And it's whether Faraday's law, you know, Faraday's law of induction, when you move a magnet inside a circuit, it generates an electric current in the circuit. And because of the changing the time-dependent magnetic flux in the loop. So he said, well, but if the wire is superconducting, there cannot be a current in it. So how do you satisfy Faraday's law? And he has been asking many people, distinguished people, including Nobel laureates at Princeton and MIT about it, and didn't get an answer. And I just thought about it, and it was obvious to me what the answer is. So I sent him a message just a few minutes later, and I basically said, in a superconductor, you basically have surface currents on the surface of the wire where the superconductivity tapers off. And these surface currents are the ones to maintain Faraday's law. And that was obvious to me. I mean, I just didn't see what's the problem. So I asked him, what am I missing? And then he made a video that received 30,000 views over a few days, just last week, about it. And frankly, I do find it strange that something that appears trivial to me, straightforward, was something that people are bothered by for a long time. And, it happens a lot to me when postdocs or even senior researchers come to my office and say, I've been working on this subject, and describe it. And then I ask them, I say, why don't you look into that or that? And they say, wow, I haven't thought about it. And then for a year or two later, they continue to work on the suggestion. So I just don't know why, but, some things appear without any effort from me. And it's really surprising. And, I wouldn't get a salary if it was not unusual. Like, if everyone would think the same way as I do, then perhaps it would be so common that nobody would pay me to be a physicist. But so I'm grateful for that. But I don't understand it, because when someone tells me something, I immediately see I immediately say something, and then it surprises me that it looks unusual to other people. I don't know why.
Yeah, no, I agree. That's maybe it's the way academia has evolved, right? Or is incentivized that we somehow lose this curiosity, right? And
well, the curiosity, and I think usually you put chains on your hands that basically you want to say something that would make others like you, and therefore you limit yourself. You restrict your imagination, and that's the one thing I avoid. I don't care what other people think. If I just say what sounds reasonable to me, and it's not just a complete speculation. I usually say something that is relevant to the question. Yeah.
Sure. So, and Ernesto has a question. Says, Professor Loeb, thank you very much for the seminar. I think the dissemination you are doing is very interesting and important. I have some questions. The first one is, what role does artificial intelligence play in the search for life? Are there robust models, or are we in a speculative stage of the data obtained from the solar system similar to ours?
Yeah, so I should say that, the way I imagine the first contact with another civilization would be not with biological creatures like you find in some science fiction stories. It's actually with an artificial intelligence system, that we will have to figure out what its intent is. And this system has its own intelligence. It's artificial, but it could be superior to human intelligence, to natural intelligence. It's artificial, but it could outsmart us. And one way to figure out what their intent is would be to use our own artificial intelligence systems, just like we sometimes ask kids to interpret content that we find on the internet because they are more computer savvy. So we will have to ask our AI systems to interpret their AI systems. And, it would be interesting to do that. But first we have to find those AI systems. So I think AI systems will play an important role in the way we interpret foreign, contact with other civilizations.
Okay, thanks. Anwar Sanchez has a question. Says, thank you for your talk, Professor Loeb. Your field is really interesting and important. I hope to collaborate with the field in the future. You have the first enrollment from a Mexican student to the Galileo project, I see here. Thanks, Axel, for inviting him to give to the talk in this seminar. More questions, colleagues? Ramon Carrillo asked, if the Oumuamua is artificial, when the senders would have information about us?
Well, so the question is, what is the intent? What was the intent of Oumuamua? And the one possibility is that it was a receiver that was collecting information. As it was tumbling around, it was collecting data. We don't know if that was the purpose of this object. And of course, the way to find out is to get more data, more evidence on future objects that look unusual, and try to figure out what their purpose is. And I should remind everyone of the story about the Trojan horse, that initially the citizens of Troy thought that it's completely innocent, but then ended up serving a different purpose. So, we should examine evidence and in figuring out what objects mean.
Mm-hmm. Thank you. More questions, colleagues? If again, you can ask directly to Loeb, to Avi, or write it on the chat. Salvador, do you have a question?
Yes, certainly. I was about to raise my hand. Professor Loeb, this has been an amazingly and astonishing, unexpected, and interesting talk, really. I really appreciate that, because it puts on our face what you said exactly, and I agree completely. We should not get blinded eyes for things that we cannot explain at the moment. And I think in one of your slides, you showed an unidentified object taken by, reported by the Pentagon. And as I recall, that kind of object suddenly appeared and then disappeared. So if that's a phenomenon which really requires an explanation, as you certainly mentioned. And we do not have, at least with the physics we know so far, we do not find any clues to explain the appearance and disappearance of those objects. Now, if that's true, then perhaps what I think is that we have only two options. One is to recognize that we must face new physics, which we are not aware about at the moment, or perhaps it's an optical kind of holographic version that has the ability to appear, disappear, but then it brings to my mind the possible ideas of remote sensing through different ways where you can approach a different world. I assume this Oumuamua object seems to be, if I'm not wrong from what I understood, seems to be a non-physically or natural constructed object, but perhaps with a different aim and constructed by different AI systems. But now, what do you think about this? I mean, are we trying to see or look for new challenges in physics, or how do we explain with the physics we know so far this situation?
I have to say that in a minute I'm expecting a call, and this question took about 3.5 minutes already. So I'll just answer very briefly. So what we need is better evidence. The evidence that was reported in the Pentagon report to Congress was not good enough. And to suggest that it indicates new physics is premature. And what the goal of the Galileo project is to collect evidence from instruments that we have full control over to figure out if indeed there is something rather unusual about such objects. So rather than worry about the data that was classified and not fully available to the public, we will try to collect our own data that will be open. And only then I would comment if there is something really unusual, because I don't know how to interpret data collected by others. For example, if you have a camera that is on a jittery cockpit of a fighter jet, then the camera may move like crazy, back and forth, and then you would think the object is moving like crazy. So it wouldn't, I don't know. I had no control over the camera, and I don't know what the object was doing. But if I'm doing my own experiment, then I can tell you what the instrument was doing, and then figure out whether the object is unusual. So I would say we should refrain from any conclusions based on the publicly available data, because it was not of scientific quality. And that's the purpose of the Galileo project, to bring it to the mainstream of science in a way that everyone can look at the data and analyze it in a reliable way. So as of now, it's premature, but hopefully within the coming years, the Galileo project will give us more confidence.
Thank you very much. Thank you very much.
Thank you, Salvador. Thank you very much. I know that you are busy, you have to take a call. So thank you very much for being here. It has been an amazing experience for me. I love your book. I'm also now reading the book of Life in the Cosmos. It took me a couple of months to read it because this is more than 1,000 pages. Thank you very much again. I recommend everybody to read his books, to follow you in the many interviews you give. Shall we thank colleagues Avi for this fantastic seminar? Thank you very much, Avi.
Thank you for having me.
Very good. Thank you very much for being here. I'll see you next time. I'll see you next week in the next seminar. Thank you again, Avi, for this amazing opportunity.
My pleasure.
Bye-bye.
Bye-bye.